My guest today is Dr. Tommy Wood, who is Associate Professor of Neuroscience and Paediatrics at the University of Washington. He also heads our research at the Food for the Brain Foundation and brain trains professional athletes, including Olympians and Formula One racing drivers. With a bachelor's degree in biochemistry from the University of Cambridge, a medical degree from the University of Oxford, and a PhD in Physiology and Neuroscience from the University of Oslo, he has approached how to optimize and recover your brain from all angles. He is also co-founder of the British Society for Lifestyle Medicine, and we really need that. And here we're going to talk about his new and first book, The Stimulated Mind, and how to future-proof your brain. Now, Tommy, welcome to my podcast.
Thanks so much for having me. I'm really excited to be here with you.
It's a major achievement. I know what it's like to write a book. You've done a fantastic job. And then there's all the references. And now there's the road show. I'm sure you're going to be traveling to the UK and all around America and doing lots of podcasts and such things. Now, I was interested in your book. You start your book with a reference to the world-renowned physician, Sir William Osler, the king of retirement. And also you say that you studied for medical school exams in Osler House, played for the Osler House football and rugby clubs, and were the head coach of the Oslo House Boat Club. But what's your take on this character out of history, Osler?
So, there's obviously many aspects to Oz's career, and he is a renowned name in medicine. Anybody who has trained in medicine will have heard of him and his sort of techniques of examination. But the reason why I talk about him in the book is specifically around his approach to retirement. The reason why I feel some connection to him, like you mentioned, is that he was a Canadian physician. He helped to found Johns Hopkins University in Baltimore, and then he was a professor of medicine at Oxford until his death in the early 20th century. So many things in Oxford Medical School are named after him, but he is kind of given credit for popularizing the idea of retirement. There's an address that he gave at Johns Hopkins now 120 years ago, where he talks about the fact that by 60 years old, the average adult is essentially useless and should be put out to pasture. I forgive him a little bit for this because at that time, the average sort of lifespan in the US was about 57 years, although some of that is dragged down by greater infant mortality, which has obviously been reversed since. But the age of the average 60-year-old back then is probably not as good as it is today. However, I think that we have embodied and absorbed this idea generally into society that by the time people get into their seventh decade, they're no longer useful contributing members to society, and individuals then embody that and think, oh, I'm too old to do this, I'm too old to learn that, and then it becomes a self-fulfilling prophecy. So I lay some blame at his feet for how we think about our brains as we age, most of which are incorrect, and we have a lot of evidence now to support that.
Yeah, so retirement's not good for you, is it?
No. There are several studies in several countries now that looked at age of retirement, particularly early retirement and risk of dementia. So retiring early seems to increase the risk of dementia, and retirement is the point at which cognitive decline maybe accelerates most rapidly in terms of sort of the trajectory of change at one time point. And this seems to be because of the loss of the cognitive and social stimuli that we receive through work. And we know that ongoing cognitive challenge and cognitive engagement is critical for maintaining cognitive function late into life and decreasing the risk of dementia. So that point at which we retire and we remove this primary set of cognitive stimuli seems to be a moment at which we're at particular risk then for cognitive decline. That doesn't mean that people can't retire. I'm not saying everybody needs to work until their death, but if you're going to retire, you need to make sure that you replace those stimuli, the complex problem solving, the social interaction that you get through work with some equivalent activities during retirement that are going to keep you cognitively engaged.
Now, if I was to give you a nickname, it would be Max Headroom. Explain your concept of headroom and the three R's.
The concept of headroom is one that sort of forms a backbone throughout the book. And it's what I call the strategy for how to maintain cognitive function for as long as possible. And then that strategy is broken down into tactics based on different lifestyle factors. But the idea of headroom is essentially to build and maintain as much capacity as is possible. This idea I've taken from an economist called Art Devaney. And in this setting, it's thinking about what's the difference between the function that I need on a day-to-day basis versus the maximum amount of function available to me. It's easy to think about this in the physical realm. So your one measure of your headroom could be what's the speed of walking or the type of movement I need just to get around on a day-to-day basis. Go up and down some stairs, walk to the shops and get some food, versus how fast and how far can I run if I really needed to. That difference would be your headroom in that kind of physical realm. So then when it comes to cognitive function, it's the difference between what do you need just to sort of like get by on a day-to-day basis versus what am I truly capable of in terms of complex skills, in terms of critical thinking, in terms of focus and attention, and how can I build that capacity as much as possible so that when I do lose some function with age, which we will all do at some point, we can't completely prevent the processes of aging yet, or when we're in situations where function tends to decline, such as when we're sick or stressed or sleep deprived, the more we have available to us, the more likely we are to maintain function under those scenarios. So if we can build function, we can build additional headroom, then we can perform better in a wide variety of things that are just going to happen on a day-to-day basis.
What are your three R's?
I was just getting to that. So the three R's are resilience, reserve, and resolve. So to go through those one by one, resilience is a neuroscience term that they generated or had to come up with because there was an imperfect correlation between what is traditionally thought to be the cause of cognitive decline and dementia, particularly Alzheimer's disease, the accumulation of amyloid and tau proteins, and an individual's cognitive function. So there are individuals who can have a huge amount of this pathology in their brains, yet function cognitively very normally. So resilience is the term that was created to define this scenario where your brain actually doesn't respond negatively to the accumulation of these proteins. You're resilient to their effect. And resilience takes a lot of forms, but something like physical activity seems to particularly build resilience. Then the next R is reserve. So reserve is essentially how much additional function or structure do you have in the system. So we know that one of the critical contributors to this is your brain volume. That is your brain reserve. In general, the more brain you have in your skull, the better, and the lower your risk of dementia, and the more volume that you maintain as you age, again, the better. Things that contribute to that kind of structural reserve include nutrient status, but also energy status. So not having what I call excess energy availability or metabolic disease, and then also not being too low and sort of chronically starving yourself, because then that can decrease brain reserve as well. And then the final part is resolve. So this is the third R. And by resolve, I really mean the willingness to continue to engage in the activities that we know contribute to headroom. So the willingness to, even as you get older, to start learning new skills, to maintain physical activity and social activity, to really make sure that you're getting all the nutrients that you need in your diet, to making sure that you get enough sleep. And that requires some, additional cognitive work. But by doing that, I think we can both build the capacity that your brain has, as well as maintain it, ideally for decades into the future.
I like your quote in the book from physicist Emerson Pugh. If the human brain was so simple that we could understand it, we would be so simple that we couldn't. And you give it in the context of your learning as you went through all your numerous qualifications, and the idea that reductionism may not be able to solve our brain diseases, and we have to think in a broader systems-based way. Can you say a little about that?
The more time I spend learning about the brain, and I think that most people are probably in this situation, even as professional neuroscientists, the more you realize how little we actually understand. And this has then resulted in the kind of the primary approach to studying the brain, which is the reductionist one. And reductionism is very common in science. It's used in the majority of scientific fields, from biology to physics. And it's this idea that we can isolate individual components of a system in order to understand the whole system. And that, in the brain, that could be individual genes, individual proteins, individual cells. And we've spent, more than 100 years now delving deeper and deeper into the inner workings of the brain, since, Golgi and Cajal first sort of described the nervous system at the end of the 19th century. They got their Nobel Prize in 1906. So after all this time and all this information we've accumulated about the brain, we still don't really know how it works. And we've also failed to develop meaningful treatments for the majority of neurological diseases that individuals suffer from. And I think, not that reductionism isn't important, not that we shouldn't accumulate information like this, but we also have to appreciate that there are aspects of brain function that cannot be predicted by just knowing about their individual components. There's this idea of emergence, which essentially says that from some collection of things and the way they interact, there are aspects and functions that emerge that you could not predict. And many of these seem to be very relevant to the brain. So, you could think about consciousness, although it's very debated what consciousness is or even where it is. But the majority of complex cognitive functions cannot be predicted from the individual components, the proteins and the genes. And how a brain looks under a microscope, which is how we diagnose certain diseases like Alzheimer's disease, how that brain looks under a microscope tells you very little about how that brain functioned in real life. So while I do appreciate the importance of accumulating this kind of information, I think that in order to address cognitive decline and dementia right now, we get much better results by thinking about stepping back and looking at the bigger picture and understanding there are a whole number of inputs that significantly improve cognition and decrease the risk of dementia, even if we don't fully understand them, even if we can't isolate all the individual proteins and genes because they act in this interactive, synergistic, emergent type way. We still have a huge amount of information so that we can act right now. And we don't need to wait to understand all these things in, minute biochemical detail before we can start to apply it to ourselves.
And that's the very positive message of your book, which we'll get into. So do you think the current obsession with the idea that accumulation of this beta amyloid protein in the brain is an example of reductionism gone wrong? Do you think there will be a drug to cure Alzheimer's? What's your prediction?
I think that the story of Alzheimer's research so far is certainly an example of where reductionism can go wrong. Again, I don't think that the research that's been done in that area is completely irrelevant. When we look at the correlation between pathology accumulation in the brain and trajectories of cognitive decline, it certainly seems that pathology in the brain is part of this whole process. It doesn't explain everything, right? That's why we had to come up with terms like resilience, but it's not completely irrelevant. However, the focus purely on amyloid and tau meant that for decades nobody was researching anything else when it came to Alzheimer's disease and dementia, and that put us on the back foot. And we're just starting to come around to this again. So, if you go back into even to the 90s, the 1990s, people were talking about the fact that yes, amyloid and tau are part of this process, but there are other things going on: neuroinflammation, nutrient status, other aspects of physical activity. Those were still sort of part of the picture. Then it sort of the field really focused down on amyloid and tau as the primary targets. That's where all the drug development went. And we've seen now, as those drugs have sort of failed to have blockbuster results again and again and again, now people are starting to zoom back out again, thinking about other cells in the brain, thinking about the environment, thinking about other exposures. And so I think we were held back for a few decades because of this huge focus on amyloid and tau. And luckily, I think that we're starting to come out the other side of that, and people are appreciating that a large number of these processes are preventable through modifiable factors, and they are mediated through other mechanisms in the brain, unrelated or not completely related to amyloid and tau. If anybody's really interested in really getting into this story, there's a very nice book by Carl Harrop called "How Not to Study a Disease," that kind of details the sort of history of where we've been in the process of trying to understand Alzheimer's disease.
And he's talking at our conference at Food for the Brain on April the 28th. And last year I interviewed Professor Jonathan Stone, and he asked a very important question, the sort of question I like, which is, why do we make amyloid? What's its function evolutionarily? And his conclusion was that it was primarily produced in order to stop bleeds. You can't have blood in the brain, a bit like you can't have water in an electrical circuit. And not only bleeds, but also infections. So his prediction was, if you rip the amyloid out of the brain, you're quite likely to get bleeds. And that seems to be honest, the major downside of these anti-amyloid treatments.
Yes, yes, absolutely. And it's thankfully a rare side effect, but is something that people are experiencing. And it's one of the reasons why not all countries have approved the latest antibodies to reduce amyloid. The other reason that amyloid is produced as part of directing neuronal connections through the processes of neuroplasticity. It has multiple functions depending on how it's cut up, the amyloid precursor protein. So yes, it seems to have antimicrobial effects. It seems to have effects related to neuroplasticity. It's produced all day, every day, and then potentially having some protective effects in terms of preventing bleeds in the brain. So it has multiple functions. It's probably there are the reasons we know that it can accumulate, such as poor sleep, right? That's the time when amyloid tends to be cleared out of the brain. But the fact that it's there is probably most of the time doing an important job. So just sort of removing it without thinking about the job that it's trying to do at the same time is probably not going to give us the whole solution to treating Alzheimer's disease. And for that reason, if that's the road we're going down, I don't think that's likely to result in a successful treatment for Alzheimer's disease. Any treatment is probably going to have to come through multiple mechanisms and include a large number of lifestyle and other factors that we know are a big part of this process.
So what is your model for understanding how to optimize brain health?
I have an idea of all the different factors related to brain health, maintaining cognitive function, preventing cognitive decline. And they've come together in this model that I call the 3S model, which is very similar to thinking about how we might build other types of function in the body, there seem to be these core processes that drive the development and maintenance of function in the brain, but also elsewhere. So the three S's are stimulus, supply, and support. When you think about any major organ system's function in the body, the stimulus applied to it seems to be the primary determinant of how it functions. So we know this in terms of physical activity, right? If you want to get fitter or stronger, stimulus or training is the most important driver of that. We also see other tissues in the body respond to stimulus to improve their function. So the immune system, if you're exposed to an infection, or if you're given a vaccine, the liver, if you drink alcohol, it gets better at metabolizing alcohol. That doesn't mean that alcohol is a good stimulus, but the body is responding to a stimulus and improving function. Bones, if we load the skeleton, if we load your bones with weight, we build more bone structure because we've sort of created a stress on the bones and they respond by improving function. The brain seems to be the same. So primary stimuli that we know build and maintain cognitive function include building social skills, motor skills, language skills, so all kinds of social interaction. And these are the critical drivers of brain development in the first place. And then seems to be really important for maintaining cognition late into life. On the other side, we see that if we remove stimuli, then we lose function. Just like if we stop exercising, then we get less fit. So social isolation, repetitive work or routines, anything that prevents us from really stimulating that tissue and being cognitively engaged seems to then decrease function. However, when we stimulate part of the brain, it needs to be able to respond to that stimulus. So the first thing that happens is more blood flow is brought into those regions of the brain that are being stimulated. This is through a process called neurovascular coupling. Basically, the neurons in that area ask for more blood flow. So the vascular system or your blood vessels need to be healthy and responsive. So that's why cardiovascular disease or heart disease risk factors overlap quite significantly with dementia risk factors, because those blood vessels need to be healthy in order to respond to stimulus. We also need to provide some kind of energy for the brain to do that job. So this is why metabolic disease or issues with energy regulation, things like prediabetes or type 2 diabetes, are also significant dementia risk factors because you're altering the availability of energy for the brain to do its job. And finally, in this bucket, this is the supply bucket, we need the nutrients to kind of run this whole system. So nutrients that we know are critical for cognitive function, and if we're deficient in them, it's associated with an increased risk of cognitive decline and dementia, include vitamin D, B vitamins, particularly those that affect homocysteine, so that's B12, folate, B6, and riboflavin, which is B2. Iron is another one. And omega-3s as well. And they all have their own role to play, and deficiencies in these can interact so that if you're just missing one, that can be enough for the system to not respond appropriately. Then the final S is support. So we've stimulated an area of the brain, we brought in a supply of all the things that it needs to do its job, but we only adapt to stimulus, we only improve function during rest and recovery afterwards. It's the same with physical training again. You don't get stronger in the gym, you get stronger when you recover and rest at home afterwards. So for the brain, the majority of this happens during sleep. So sleep is probably one of the most critical components of this support bucket. But there are other things that can support this adaptation. So there are factors, trophic factors that are produced during exercise, for example, like brain-derived neurotrophic factor that can support neuroplasticity and adaptation in the brain. There's also hormones that we know act as trophic factors or support factors in the brain, so those are important too. And we also want to avoid things that can impair this adaptation. Anything that causes chronic inflammation, like gum disease or air pollution or smoking, and excessive use of alcohol can have a similar effect here. Then something like chronic stress as well can prevent the brain from sort of truly switching off and shutting down and being able to respond and adapt. So that kind of makes up my support bucket. Now, all of these buckets, they're not separate lists, they're all interconnected. And so if we stimulate the brain, it drives greater sleep need. We've seen studies in older adults who do some kind of cognitive training. They sleep better because the training then tells the brain, I need more time to rest and recover. So what that means is you don't need to think about addressing all of these things at the same time. Of course, they're all important. But when you change one, you change multiple things at the same time. So if you routinely sleep for 6 hours a night and you start to sleep for 7 hours a night, all of a sudden your blood pressure improves and your blood sugar improves and maybe inflammation comes down. And the next day you feel more social and you also feel like you're more willing to engage in cognitively stimulating tasks or cognitively challenging tasks, which we tend to avoid when we're tired. So we see this regardless of where you enter the system, because they're all interconnected and they influence one another. If you just start with one thing, the whole system starts to shift in your favor. And yes, there may be other areas you need to address as well, but they all sort of come together and you can build on them over time.
What is the best way to stimulate your mind?
The best ways to stimulate your mind, I think I always go back to the types of complex cognitive skills that feel very human and that we've been doing for millennia at this point, sort of like almost part of our evolutionary process. So we can do things like brain training on a computer, and there's some reasonable evidence for very specific types of brain training that can help to stimulate the brain and decrease the risk of dementia long term. However, I think more complex cognitive stimuli that come from how we engage with the environment probably have an outsized effect. And we see that throughout the literature. So we're talking sports or movement activities that have complex multisensory stimuli involved. So you need your vision and your hearing, and you need to process information quickly, like this ball that's being hit at you, or trying to plan the movement you're going to do in a dance class. And they often have a social component as well as a physical activity component. So these kind of complex sports, what we call open skill sports in the research, ball sports, team sports, board sports, dancing, martial arts, they seem to have particular benefits for the brain because you've got a physical component, but you're also cognitively, you're stimulating multiple systems and networks within the brain. Then anything related to social interaction seems to have a big effect. The importance of pro-social behavior, but also just interacting with others is a critical stimulus. Then thinking about other related activities that humans kind of do in groups or that are really important to our development. Languages and music come up frequently. Some of the creative arts now have an increasing amount of evidence to support them. So say painting or drawing or some of these other ways that we creatively express ourselves, that requires the accumulation of skills, but then also the expression of those skills, and often in a social setting. So those are the things, those kinds of activities are, I think, the ones that have the biggest return on investment in terms of really stimulating your brain from multiple angles.
Yeah, I'm a little bit freaked out because I'm 68 and I've got to pass a meteorology, aerodynamics, and air law exam to finally get my paraglider flying license.
Uh-huh.
It's complicated stuff.
Yeah.
But today in the Black Mountains, where they train military planes, this old bomber came over, and I think one of the reasons we have to learn all this stuff is you have to be able to look and see, because it's posted, when some Chinook helicopter is likely to fly right by where you're paragliding. So the motive is good.
Yeah.
Anyway, how important is physical exercise, and what's building muscle got to do with it? I know you have great big biceps.
Well, I think all the things that you're doing right now. So both the fact and skill learning that you're doing for these new skills that you're developing, right? I think you're doing exactly the kind of things that human brains benefit from, regardless of age. So I'm glad that you're engaging with that, and obviously avoiding colliding with a helicopter is probably a good idea. In terms of physical activity, there's very strong evidence that the general function of most of the tissues in the human body is supported by physical activity. Physical activity is probably the only thing that we know of that addresses all of the hallmarks of aging. So these processes that happen in tissues as they age that we can measure biochemically. A lot of that we can only do in mouse and rat studies or animal studies so far. But there seems to be these core processes that happen as we age, including in the brain. And physical activity either slows or prevents or maybe even reverses many of them. So we see across a broad range of different studies that different types of activity have different effects on the brain. So broadly, just moving more during the day, the more steps you take, for example, up to somewhere between 8 and 12,000 steps a day, the lower your risk of dementia. And it's in that range is essentially linear. So more is more, up to somewhere around an hour or two of just general moving around in the world. We also know that particularly if we're not physically active, then people who start an aerobic training program, they start to see improvements in the structure and function of the hippocampus. So the hippocampus being a part of the gray matter of the brain that is critically important for forming memories and is affected in the later stages of Alzheimer's disease. So the best known study of this was done now more than 15 years ago. Older adults did a brisk walking training program, 40 minutes, 3 times a week for a year. They saw an increase in the size of their hippocampi compared to a control group who actually had an age-related decline in hippocampal size. And with that, they saw improvements in memory function. There was another study more recently that shows that these benefits of exercise on the brain are probably intensity dependent, meaning that the more intense exercise you do, some of the better results you'll get. So this study randomized 3 different, again, older adults in their 60s and 70s to 3 different groups. One group was sort of a control group, and they didn't really do much exercise. The second group was like a jogging group, did 40 minutes of jogging 3 times a week. The third group did high intensity interval training on a treadmill. So they ran essentially as fast as they could for 4 minutes. Then they rested for 3 minutes, and they did that 4 times over. This is a protocol called the Norwegian 4x4 protocol. They did that 3 times a week for 6 months. What they found was that both the jogging group and the interval training group improved fitness by a similar amount, but there were much better improvements in hippocampal structure and function in the interval training group. And these benefits were retained for 5 years after the end of the study, even after they stopped training in that way. So there are a whole host of factors that get released during exercise, and more are released when that exercise is particularly intense through something like interval training, that then have additional benefits in terms of brain structure and brain function. All of these sort of aerobic type exercises, so from brisk walking through to sprinting, they seem to particularly benefit the gray matter of the brain, so the outer cortex, the hippocampus, and generally seem to support memory, so memory function. By comparison, resistance training, so this is where we finally get to the biceps, resistance training seems to be particularly beneficial for the white matter of the brain, which sits in sort of in the middle of the brain. It's where all the fat in the brain is, or most of the fat in the brain is, and it's responsible for really fast connections and some of our most complex cognitive functions like executive function and decision making, as well as focus and attention. And randomized controlled trials show that if you start somebody on a resistance training program, so now 2 times a week you go and you lift weights, you do a few different exercises, maybe 6 different exercises that cover the whole body. So some pressing, some pulling, some squatting, or some deadlifting. You do that for 3 sets of 8 to 12 repetitions twice a week for 6 months. You see significant improvements in the structure of the white matter, and with that, you see improvements in executive function. So what you then need to ideally do is a bit of both. So you're moving around frequently during the day. Occasionally, you're doing some sprinting, and then a couple of times a week, you're doing some kind of resistance training. The final piece is that, as I kind of mentioned earlier, coordinative exercise. So these types of sports or movements that require both a physical component but a cognitive component as well, they seem to have an outsized benefit beyond just the physical side of them. So dancing compared to circuit training, or badminton compared to cycling, you get a slightly greater cognitive benefit if you're doing these complex coordinative movements above and beyond the physical component. So that kind of says, when you're doing your jogging or cycling, if you can occasionally or regularly replace those kinds of sessions with something that's more complex from a motor skill component, or has a social component, you're probably going to get additional benefits. So join a dance class, join a paddle league, go learn a martial art, as long as you're not getting punched in the head, which we know is bad for your cognitive function. Those kinds of things are going to have an outsized benefit. So regularly move. If you can do it in a way that requires you to learn a new skill in a social setting, and then twice a week do some kind of resistance training and move really, really quickly in sort of a sprint type approach, that's going to give you this broad whole brain sort of supportive physical activity kind of program.
How adaptable is the brain? Is it ever too late?
No, as far as I can tell, it's not too late. The only situation when it may be too late is in the late stages of cognitive decline and dementia. There are some suggestions that Alzheimer's disease or dementia is fundamentally a loss of neuroplasticity. So it's a loss of the brain's ability to forge new connections and maintain them. And this probably happens at some point in the very late stages of dementia. Up until that point, adult human brains show the ability to adapt to experience neuroplasticity and improve both structure and function into their 70s and 80s, at least, as long as the correct stimulus and environment is applied. So for the vast majority of people, it is never too late to start.
It wasn't so many years ago where the general thinking was you can't build new neurons, but here you're talking about neuroplasticity as connections. I mean, how quickly can we make new connections in the brain?
This is one of the reasons why I think we fundamentally developed the wrong idea about what it means to build and maintain brain function as adults. So there are two different aspects to this. One is neurogenesis, so the making new neurons. And this does happen in some areas of the adult brain, even all the way up until death. But not in the vast majority of the brain. So it happens in one particular part of the hippocampus, the dentate gyrus, and it happens in the olfactory bulbs, where we sort of generate signals of smell. Everywhere else, your brain essentially stops growing new neurons in early childhood. After that, all of this is about neuroplasticity or synaptoplasticity. So it's the generation of synapses and connections between neurons and all the supporting structure and cells that are other cells that are part of that. So neurons only make up about half the cells in the brain. The other half are oligodendrocytes, microglia, astrocytes, all the blood vessels and the endothelial cells that make up those. They form critical parts of this structure as well, and are also remain adaptable and for decades for our entire lives. So we thought that because we can't make new neurons as adults in most of our brain, then our brain can't change. But that's just inherently wrong, because the neurons that we do have and the structures that support them remain adaptable and plastic, as we call it, essentially for our entire lives. And so anytime you're experiencing a new skill, new information, you're learning anything, you're experiencing anything. Essentially, synapses are being refined and built in your brain the whole time. So we're doing this continuously. But in order for them to be created and then cemented in a way that helps to build and maintain structure and function requires then this whole host of things to come together. So some kind of stimulus, ensuring nutrient status and cardiovascular health are good, plus then the sleep and support that kind of requires that final cementing of structure to happen. So we are making new synapses all the time. It's whether we have all the things in place to make sure that then results in improvements in both structure and function in the brain.
There's a section in your book called Nourish. And of course, earlier you mentioned the importance of vitamin D, omega-3, B vitamins, and so on. What's your key message on the nourishment front? And I'd be very interested to know what supplements you take.
One thing that I've really learned about diets over the years is that anytime anybody says that this one diet is the thing that you should eat, there's plenty of evidence to suggest that other people are eating a different way and they're doing just fine. So I very much have a broad approach to diet. And I think about three main levers that we can pull in terms of diet. So the first is nutrients. I think I call nutrients the great leveler because we know that they're critical for brain function. We know that they determine our risk of cognitive decline and dementia. But as long as we get them, I don't mind where we get them from. And then I think that opens us up to thinking about, well, what's the kind of diet or supplement strategy that I might need to make sure that I get those nutrients because they're really a critical foundation. Then I think about energy. And like I mentioned earlier, we need adequate energy status to support brain reserve in particular. And this means not chronically restricting ourselves, which some people have kind of called for in the anti-aging or longevity sphere, even though there's very little evidence for that in humans. But then also avoiding overeating that can result in metabolic disease, types of diabetes, high blood pressure, cardiovascular disease. So we want to eat a diet that is nutrient dense, that avoids high calorie density or overeating. And so then my third lever is pattern. So what's the overall pattern of the diet that allows you to achieve those two other things? And in general, this is usually a whole foods based diet that's more nutrient dense, less calorie dense, more satiating because it has more protein, more fiber, more water, more nutrients. And that makes it more likely to be sustainable. But there's obviously a whole different range of foods and ways that you can achieve those things based on your own personal preferences. So if you're achieving all of that, ideally, you wouldn't need to supplement. You're regularly eating seafood for your omega-3s. You're either getting sunlight or seafood or maybe fortified dairy gets you vitamin D. If you're eating leafy greens and meats and seafood, right, you're going to get your B vitamins. If you're eating eggs or liver, you'll get choline, which is another critical sort of structural component of the brain. So hopefully some kind of omnivorous, nutrient-dense diet gets you to all of those things. If that's not the case, or your diet doesn't look like that, or ideally maybe you get some kind of test to see that you don't have adequate status of those things, then I think supplementation is the right way forward. So a good B vitamin supplement or a fish oil or omega-3 supplement. And so the things that I take personally, I generally take an omega-3 if I haven't regularly been eating seafood, which just sort of like happens sometimes. But usually I eat seafood 2 or 3 times a week, so I don't need to supplement with omega-3s. I'll take a vitamin D supplement in the winter. I supplement with creatine, which has some interesting potential cognitive benefits. But for me, particularly, it's from an athletic performance standpoint. I take magnesium at night because magnesium, like athletes and most people actually don't get enough magnesium from their diet. It can also help to support sleep a little bit. And most of the time, that's essentially it.
Yeah, I spent a month in the winter in a very sunny place in Kenya and
Mm.
generally supplement uh, vitamin D, for example, in a
Yeah.
multivitamin. And still, I was just at that 75 nanomole per liter level, which is adequate. There's no question about that. But from the research I read, I might want to even be a little bit higher. And then my wife and I had a homocysteine test, and we eat
Hmm.
the same food. Mine was 7, and I only supplement 10 micrograms of vitamin B12. I think a lot of people don't get enough B12.
Yeah.
Hers was 15. So she's now supplementing 500 micrograms, which is sort of over 200 times the RDA. And she's brought her homocysteine down to 8. So how important is homocysteine? Because it does seem that some people on very good diets, especially later in life, don't have a good result, which we would say is over 11 micromole per liter.
Yes. So yeah, just to clarify, a not good result is over 11. A
Yes.
good result is less than 11.
Yes.
So I think homocysteine is critically important. This is something that you and Food for the Brain have talked about for long periods of time. Thinking about multiple studies now that show if you have elevated homocysteine, you have a higher rate of atrophy or loss of brain volume, as well as a faster rate of cognitive decline. And this is at least partly dependent on omega-3 status, right? So if you have high homocysteine and you treat that with B vitamins, but you don't have good omega-3 status, you won't benefit from those B vitamins and lowering your homocysteine in the same way. If we think about this in a reductionist way, we think that homocysteine has some direct effects on the accumulation of tau in the brain. So we know both from actually measuring things we care about, brain volume and brain function, and potentially some of the mechanisms as well, that homocysteine is a critical part of this system if we're thinking about trying to maintain cognition long term. And you're right that this is one reason why testing can become critically important, because you may assume that you're getting enough B vitamins from your diet. But I think unless somebody is eating a lot of seafood, a lot of meat, it's quite likely they may need to supplement, as you said, particularly as people get older. So homocysteine, we know, I think the evidence is very good that it's a significant risk factor, and if we can test and address that, we know that also slows the rate of cognitive decline, and will be expected to significantly reduce the risk of dementia.
Now, tell us a little about the research that you're very much involved with at Food for the Brain, which is it's using the 5-in-1. It's called the Drift test. It's a home test kit. It measures your homocysteine, your HbA1c, which is to do with blood sugar balance, omega-3, vitamin D, and also the glutathione index. So, where is this research headed? Do you think combinations of these kind of biomarkers are going to be important for preventing dementia?
Absolutely. We already know from some other studies that having multiple nutrient insufficiencies or deficiencies significantly increases the risk of dementia, and they kind of stack up on top of each other. And some, particularly homocysteine and omega-3 status, they're dependent on one another. So you need both to be good in order to benefit. And I think we'll probably see more of that just as we collect the data, because each of these nutrients has a different role in the process of sending a signal along from one neuron to another in the brain. And so if you just have one missing link, that essentially that could affect multiple downstream processes. So at Food for the Brain, the Drift test has been put together. It's like an at-home kit where people can measure these things, and we know the cutoffs and target levels that are associated with lower risk. We know what people can supplement with in order to improve that. And so the first goal really is to look at how do these nutrient markers and glutathione, so our antioxidant status, how do they relate to cognitive function in the general population. If you look at people across a wide range of ages, men and women, based on other risk factors, things like educational status and socioeconomic status, we know those are very important too. How do these different nutrient markers relate to cognitive function? And then over time, as we collect more data, we can look at how do these markers relate to change in cognitive function in a given individual over time. And ideally be able to show or at least understand better how what levels are most important, how the supplementation change responses. And this takes large amounts of data. This would ideally be tens or hundreds of thousands of people repeatedly taking the test over time, so we can really understand these trajectories, understand what people are doing, whether they supplement, when they supplement, how their brain and body and nutrient levels respond. And so, like, we're right at the beginning of trying to understand just what does it look like when people do these tests, and how does that relate to their cognitive function? And then ideally over time, we can understand how these things influence individual changes in cognitive function in people as they get older.
And if there's anyone listening who hasn't done the free cognitive function test at foodforthebrain.org, ideally also doing the blood test, drift blood test, please do, because that's how we get this data, all anonymized. That's how we can do this research. Now, there's a lot of noise about a blood test for dementia, and it looks like the front runner is the ratio of a type of amyloid 42, and a type of p-tau 217. In fact, one company already got a license for this test. Mm-hmm. Is this the way it's going?
It is the way it's going, and I think there is some potential benefit there, but we still don't really know how to use these things at a population level. So right now, if you measure the ratios of different amyloids, 42 to 40, and certain tau levels, so particularly tau, p-tau 217 in the blood, they're very good at telling you how much amyloid and tau is in the brain, for example. And so one reason why you develop these is that you would then target amyloid and tau in the brain with a drug, and then you would see these blood tests respond. I don't think, like we talked about earlier, that's necessarily going to be the place where we see the biggest impact. There was a recent paper that looked at trajectory of p-tau 217 in individuals over time, and you could see those who accumulated p-tau 217 more rapidly, then it was quite accurate in terms of predicting later dementia onset. Because p-tau 217 is related to a whole, because p-tau 217 is related to a number of different factors, not just amyloid. That's probably the test that seems to be, if there was a better test, that one seems to be more accurate in terms of determining dementia risk. However, there have been studies that have looked at multiple markers, such as amyloid and tau, but also GFAP, which is released by astrocytes, and NFL, neurofilament light, which is released by neurons in the setting of some kind of injury or neurodegeneration. And in one large study, they looked at all the levels of these different markers, and then even when they picked the cutoffs for combinations of these markers, they could only find a combination that could predict a high risk group. And that high risk group, only 43% of them got dementia over the next 10 years. So they're certainly not perfect yet. They're still a long way away from being really good at predicting who's going to get dementia. And the main issue, well, two main issues. One being it's obviously an overly reductionist approach. We're going to assume that these one things are the main drivers, and we're going to try and develop drugs to target just those things, when all the other stuff we've already talked about today seems to have a much larger impact. But nobody knows yet what to do with the results of these tests in individuals who are not experiencing any kind of cognitive decline yet. So I worry that there's going to be this period of time where we're going to get a lot of overdiagnosis. We're going to get a lot of very worried people. without really knowing what to do with the results of these tests. There are some preventative neurology clinics, at least in the US, and I'm sure around the world, that are taking individuals, looking at some of these tests, and then addressing lifestyle and other risk factors, and potentially seeing some positive changes, right? So reversal of some of these elevated risk markers like p-tau 217. But we were like right at the beginning of that. So I think there could be some utility in identifying high risk people if that's then used to help those individuals make lifestyle and environmental changes that we know, significantly would decrease their risk of dementia. That seems like a reasonable approach, but we don't really understand exactly how to understand these tests yet in the general population. So I worry that there's going to be this period of time where lots of people are using them, nobody understands them, nobody knows what to do with them, and that's just going to end up worrying a lot of people and costing a lot of money. So there's still a huge body of research that needs to be done to understand who these tests are useful in, how they're useful, and how we should intervene in response to a specific result.
And p-tau, this phosphorylated tau, is very much associated with homocysteine, lack of B vitamins. So there are things that we can do. Now, your model, you've already spoken about the importance of reducing stress, sleep, very important, social interaction, very important. What's your take on coffee and caffeine and also alcohol? I read a recent study where it seems like a small amount of coffee, caffeine, is good for you, but a large amount, and by the way, we know it raises homocysteine a lot, is not. Same with alcohol. What's your view?
Yeah. Yes. So I think we consistently see in the literature that moderate amounts of coffee and tea are associated with a lower risk of dementia. So that's like 2 to 4 cups a day. We do also know that caffeine can negatively impact sleep. And so there was one study that didn't look at dementia, but looked at mortality risk and found that those who drink coffee just in the morning have a lower risk of death, but those who drink coffee throughout the day don't. It doesn't have a negative effect. It just has no net effect. And this is probably because then caffeine is impacting their sleep, or they're not sleeping well enough, which then makes it so they have to drink coffee throughout the day. There's potentially a direct effect of caffeine there. We in many settings, caffeine is neuroprotective. We do some studies in my lab with caffeine as a neuroprotectant. But there's also a large number of polyphenols and antioxidants in coffee and tea that are likely to be beneficial. Coffee in the Western world is the major source of antioxidants in most people's diets. And in some studies, you see this. So if you drink decaf coffee, you still get many of the benefits of coffee drinking. So as long as it's not impacting your sleep and it's a moderate amount, 2 to 4 cups a day, then I think there's a potential for a net benefit there. For alcohol, I think what we really know about alcohol and at this point is that most of the studies that previously suggested a moderate amount of alcohol drinking decreased the risk of cardiovascular disease and death and dementia. Most of those were probably confounded by a healthy user bias and how they counted those who didn't drink at all. So the people who didn't drink at all were a combination of those who didn't drink for a variety of reasons, including some health reasons, and those who used to drink too much and were now teetotalers. And so that kind of no drinking group was pretty murky. And so then anybody who drinks just like a little bit ends up looking a lot healthier. When we fully account for that, most of those effects go away, though not all of them. So if you drink, 2 or 3 times a week on average, one drink, you have a slightly lower risk of cardiovascular disease, but that's balanced out by a slightly higher risk of certain cancers and strokes. So the overall net effect on mortality risk is essentially zero at that kind of level of drinking. Once you're above one UK drink a day, so 1 unit a day, you start to see smaller brain volumes and a higher risk of dementia. So in general, I think that one or two drinks once or twice a week is probably okay. Anything more than that, I think we start to see an increased risk. This is for a variety of reasons, including the fact that alcohol causes a REM sleep deficiency, so it can negatively impact how good quality our sleep is. So I don't think that everybody needs to be a teetotaler, but I also don't think that everybody should be drinking every day or binge drinking. But the occasional nice glass of wine or cocktail in a social setting, all of that stuff, I think is absolutely fine.
Now, on that sober note, we've touched on a fraction of the pearls of wisdom in your brilliant book, The Stimulated Mind, which is out on March the 26th, available from foodforthebrain.org, and do support your local bookshops by getting them to stock it. Dr. Tommy Wood, thank you very much for being my guest and sharing your wisdom in how to keep our mind and brains super sharp and stimulated.
Thanks so much for having me. I really appreciate the opportunity to talk about all of these things and just spend time with you, Patrick. It's always a treat. And thanks so much to everybody for listening.